Hello everyone, welcome to an algebra video tutorial. We're going to be working on graphing exponential functions. So we've got two functions here. We've got a blue function, f of x equals 5 times 1.2 to the x power. And we've got g of x equals 50 times 0.8 to the x power. And we're going to take both of these exponential functions, they're exponential because my independent variable is the exponent. And we're going to see what the graphs of both of these functions look like. Talk about the graphs, do some comparison, just doing graphs by hand. Hopefully you also have a graphing calculator or you're using some graphing program on your computer or tablet to do this for you as well. But there's something good about graphing by hand to understand what it is a graph actually represents. So get your calculators handy, however, because we first got to make a table of values to get some points that we can plot. So here we go. Let's start with function f of x here. So I've picked some x values. I just chose some x values at random, a few negative, a few positive, and make them kind of evenly spaced here because it's going to help me understand the pattern as I look both at the table and the graph. So we're going to start by just putting in these x values in for my exponent, calculating it all out, and see what I get back for my functions, my output values. So in the first case, if I take 5 times 1.2 to the x power, if I put negative 3 in, we get 2.89352. If I put in negative 2, we get 3.47222. If I put in negative 1, we get 4.16667. Now I'm assuming my calculator is probably rounding some of these off, especially if I'm noticing some variables there. So you can change your calculator settings to see more or less digits or round it, whatnot. But it's going to give us enough to understand the pattern, do some graphing. To the 0th power, this one's easy, but I can go ahead and put in 0 in my exponent. 0th power just gives you that value for a, so it's going to be 5. If I put in 1, we get 6. If I put in 2, we get 7.2. And finally the last one, if I put in 3, we get 8.64. All right, let's go ahead and graph these points now. I'm going to go ahead and scale it kind of interesting just so I can fit this other graph. I noticed it has a starting value of 50. So I'm going to want to make 50 to be able to fit on this graph. But we're going to do for our x value, for x-axis, let me change colors here. There's our x-axis right there. Each one is going to represent 1. So there's 1, 2, 3, 4, 5, 6, and so on that way. And down here is negative 1, negative 2, negative 3, negative 4, negative 5, and negative 6. So I'm scaling my x-axis by 1s. But for my y-axis, I'm going to scale it by, let's see, I think it goes up by 10. I'm going to go ahead and scale it by 10s. So, well, let's go ahead and scale it by 5. So right here will be 10. So 5, 10, 15, 20, 25, 30, 35, 40, 45, and up here is 50. Same thing down here, there's only negative, so negative 10, negative 20, negative 30, and so on. All right, let's graph my blue graph here now. So we've got some values. If I go to negative 3 and up to 2.89, that's going to be right about there. It's less than 5. I approximate it as best I can. Over at negative 2, negative 3.47, it's a little bit bigger, but it's not that much bigger. At negative 1, we're getting 4.16. It's close to 5. At 0, it's exactly 5. There's my y-intercept. One thing to point out, we've always called this the starting value. When x is 0, it gives you the value of a. We can also call it the y-intercept now. We can see on the graph, that's where it crosses the y-axis. So that makes it a really handy point to find. Okay, if I put in 1, I get 6. put in 2, I get 7.2. And 3, I get 8.64. All right, just for kicks, since this goes all the way up to 10, well, let's put in 10 and see what number we get here. I'm going to put in 10 for my function. So 5 times 1.2 to the 10th power, and we get 30.98587. So if I get all the way to 10 out here, now all of a sudden we've made it up. 30.9 is right about there. So what can we conclude? If we kind of look at the dots, again, a graph represents all the possible points. So we just found 1, 2, 3, 4, 5, 7, 8 of them. But if we were to pick 1,000,000 dots or 1,000,000,000 dots, there's an infinite number of points because there's an infinite number of x values I could put in. So we draw a line to say, okay, well, the dots represent the trend, but really there's all these points along here. So we're going to use a curve. And with that 30, it's roughly going to be something like this. Oh, that's a bad little stretch part there on the left. All right, there we go. And there we go. We've graphed our first exponential function. It's a little bit different than a linear function, huh? So first of all, you notice it's curved. So exponential functions are generally either growing or decreasing, and they're curving as they're doing that. So we notice it's not growing very much in my table, but all of a sudden if I go all the way up to 10, now it's really, it somehow grew a lot there. We could fill in 4, 5, 6, 7, 8, or 9 for the x values. And we can see that it's starting to increase how fast it grows. That's a sign of exponential growth right there. So we have a nice curved function. If I kept going, we would see that it would increase as high as I want. So that's kind of an interesting thing to note there on the graph. We're going to talk more about what we call end behavior as we go on and on forever in either direction. There you go. We graphed some points. This one is exponential growth. So I'm going to call it growth. Because we're starting with 5, but I'm getting bigger, 1.2, and my graph seems to be growing. Okay, let's look at the red graph. Let's take a look at this one. We're starting with 50 and multiplying by 0.8 over and over again. So let's do some math on this one. 50 times 0.8 to the negative third power, and we get 97.6563. Now let's take it to the negative 2 power, and we get 78.125. To the negative 1 power, we get 62.5. There's my 0th term, or my 0 value for input. That's going to be my y-intercept. It's just going to be 50. If I put 1 in, we're going to get 40. I put 2 in, it goes down to 32. And finally, for an input of 3 into my exponent, we're down to 25.6. All right, let's graph these points. Well, the first 3, I can't fit those on my graph, right? We scaled it up to 50, so I can get 0, 50. I'll plot that point here. And I could probably stretch at negative 1, 62. You know, it's roughly going to be out here somewhere if I kept going up high to 60. But we have a couple that they don't even fit on the graph. So exponential functions grow very fast. And a lot of times when you're trying to graph them, it's hard to fit them as nicely on a scale. We even scaled the y-axis by 10 or by 5 for each block, trying to be able to have more room to fit points, but we still can't fit them all in this case. So keep a note of that as you're trying to graph functions. But we can get 1 is at 40, so let's plot that point. 2 is at 32, so right about there. And 3 is at 25, so right about there, 25.6. And then just for kicks on this one, let's also go all the way out to 10 and see if anything kind of decreases or is really different when we go farther out. So at 10, we get, if I input 10 for my x value in the exponent, I get 5.36871. So 10 will be out here, 5, and it somehow bounces all the way down. So now let's draw a curved line representing all the points. Again, we graphed some points to get an idea of the curve, but now we're going to do our best to kind of freehand connect them. And look at that. So it's also a curved line. Again, this is a horrible freehand job, but I think hopefully you get the point. It's a decreasing graph, and in exponential forms, we call that exponential decay. Anytime we have a graph, if I go to the right, this is losing value, right? It's decreasing. It's slowing down as it's decreasing, but it's still decreasing. We go from 50 to 40 to 32 to 25. We're going down in our values. Whereas in the blue graph, it was growth. We're getting bigger in our values. So as you're doing graphs, keep a note on, is my graph increasing or is it decreasing? Is it an example of exponential growth or is it an example of exponential decay? Here we've just got a couple examples, and we draw the line because we can put in any x value and we need to represent all the possible points that fit our exponential pattern. So I could find any of these point values, as many as I want. We just pick a few convenient ones to be able to graph some points to get an idea of where my curve is going. All right, hopefully that's a good introduction for graphs and being able to see graphs. We're going to explore some more with using a graphing program to help us understand and look for some patterns a little bit easier. But there you go. Hopefully that's a good start for you.